In this lecture, we will be discussing pH, pOH, kW, and all of the different types of components that are related to pH and how to calculate to and from it. So let's get started. So we're dealing with water, and water, unlike a lot of covalent compounds, loves to self-ionize. So I have my liquid water, and it does self-ionize into a proton and a hydroxide. Now it doesn't do it that much, and I know that because it has something, a K equilibrium constant. And that K equilibrium constant is 1 times 10 to the negative 14. Now as we know, KQ is equal to essentially the concentration of the products over the concentration of the reactants. Being a very small KQ means there's a huge amount of reactants compared to products when we've achieved that equilibrium position. So I should draw this as a double arrow. So that means this Kw being very small, that very little water self-ionize. We call this reaction an auto-ionization reaction. And again, I'll write that in. So auto-ionization. But regardless, it doesn't happen that much because the equilibrium constant is so small, reactants are favored. Now I could write this another way. Probably a better way to write this, okay, would be to take the 2 water molecules instead of the 1. So 2 water molecules react, come together, and what happens with, and of course we're at equilibrium, one of the water molecules will donate a proton, which we'll learn is acting as an acid. And when that happens, it produces a hydroxide. And the water that is accepting the H is acting as a base, as we will learn when we get to those definitions. But right now, we'll know that that becomes H3O+. Now whether we, and this is aqueous, this is also aqueous ions. Now, whether we write it this way or this way, it's the same thing. Meaning that our H plus here and the H3O plus are synonymous. So whether I talk about the proton or the H3O plus, which by the way is called the hydronium ion, and that's given to us in our reference table. What the heck is that? Table E. This of course is hydroxide. They sound similar, but they're different. So hydronium, or the proton, and the reason why we call H plus a proton is because if you think about it, hydrogen has a mass of 1 and has an atomic number of 1, which means as an atom it has 1 electron and 1 proton and 0 neutrons when you subtract. So we've got a proton surrounded by an electron. Now when it becomes positive 1, it loses that electron, and what you're left is a proton. Okay? Very positive, high charge density, and highly reactive. Now the reason why we write the second reaction usually, because the first one, the idea that you have free protons in water would be highly unlikely, as they'd be absorbed by water acting as a base. As you can see, it acts as a base and an acid. But we call it amphoteric. Okay, and we'll get back to those definitions, but that's for a later date. So back to where I'm talking about here. So what I have here is the concentration now of H plus or H3O plus. These are synonymous, or I have hydroxide. So water breaks apart into a hydroxide and either an H plus or H3O plus. Does not matter. Now we know the KQ is equal to 1 times 10 to the negative 14. Because this is for water, and this is a very important reaction, we write Kw. And again, it's 1 times 10 to the negative 14. All right, so Kw is what we use to show that this is the equilibrium constant for the self or auto-ionization of water. Now, like all KEQs, they're equal to something called the law of mass action, or the equilibrium expression. And we have learned that KQ, or in this case Kw, because it's for water, is equal to the products over reactants. The coefficients become exponents, and the solids and liquids don't apply. So let's write our coefficients. I'm sorry, let's write our products, H plus and hydroxide. And what I'll do is, just to make sure that we are understanding that we're dealing with H plus and or H3O plus, I'll put this in here to remind you it could be either or, times the concentration of the other product. Notice they're to the 1 power because there's a coefficient of 1 there. So that's what I have here. Now, if you notice, it's products over reactants. But our reactants, okay, as we can see, have what? Liquids. Solids and liquids don't apply because they don't have a concentration. So just like a KSP, we're left with the ions. It's like a solubility product for water. But we call it KW because we'll use it for different reasons, as I will show you now. What is this KW? Well, as we just said, it's equal to 1 times 10 to the negative 14. Okay, now let's do some stoichiometry. For every 1 water, how many protons and hydroxides to form? Well, as you can see, every one of these you produce 1 H plus and 1 hydroxide. So it should make sense to you the amount of ions for each should be equal, right? For every one we make 1 of these and 1 of these. So therefore, there should be an equal amount of hydroxides to H pluses in pure water. All right. Now, we know that the KW, which is the value of KQ, which is an equilibrium constant, is equal to the values of these things at equilibrium. So, if these are equal, the hydroxide and the H plus, if they're equal values, what two numbers multiplied together that are the same will equal this? I'll say it again. What two numbers, when multiplied together, that are the same number equal 1 times 10 to the negative 14? If you haven't already guessed, it's 1 times 10 to the negative 7 and 1 times 10 to the negative 7. These brackets that I'm drawing here represent concentration. So it's a molarity. And you say, well, how do I know that? Well, when we multiply numbers, the what? You add the exponents. All right, and they have to be the same because 1 water makes 1 H plus and 1 hydroxide. That's how it works. So in pure water, these have to be equal. Now, if you notice, these concentrations are very small. They have to be because KEQ is very small. For instance, the concentration of the H plus or the H3O plus, the hydronium ion, is 0.0000001. That's what this scientific notation is telling us. All right, and the same thing for the hydroxide. This is the hydroxide concentration, which will also be 0.0000001. Very, very, very small, obviously. Now, what we're going to do is, you've noticed in previous courses that they like to take small numbers or very big numbers and convert them into scientific notation. Well, what we're going to do is we're going to take this number in scientific notation and we're going to stuff it into an exponent, base 10. So we're going to make it into an exponent. Now, why do we want to do that? Why do we care in the beginning? Well, I'll tell you why we care. This balance of H plus, H3O plus with hydroxide is so very important in so many reactions. It triggers so many different things. And H plus is highly reactive. As I mentioned, it's a proton, it's positive. That's like a heat-sinking missile for electrons. And where are their electrons? Well, between what? Between chemical bonds, there's electrons. So these protons love to break and suck up electrons, and that's why they break bonds and can be so corrosive. Who else has got electrons? As you've talked about before, metals do. Metals have electrons they freely give. So metals can get corroded into ions. Ions have different strength and different type of structure than the metal atoms. So acids can cause all kinds of damage to our physical world, but they also are very important in understanding how they are reacted or involved with enzymes and proteins and very organic type of reactions that are in our body. We have a very, very, very balanced chemical process in our body. Homeostasis has to be at a certain value of these, because if you have too many or too less, it will cause unforeseen damage, homeostasis can't occur, which means the body can't run under adverse amounts of swings of H pluses. So even our breathing is maintained by this amount of proton. If we don't have a lot of protons, or at least the proton amount or concentration in our blood will trigger our body to breathe. We can't force ourselves to hold our breath and commit some unforeseen problem for ourselves by holding our breath, because the autonomic nervous system will come in. Our body will trigger breathing on its own by this proton concentration. So it's very important to measure this. Life cannot exist unless the ratio of these two is at a certain level. So it's important to measure. So what we're going to do is we're going to measure the H plus ion concentration. And to stuff this entire thing into an exponent, what we're going to say is we're going to make the log of it. Now the log is a base 10. There's different types of logs, but we're going to use a base 10. This is already in a base 10, so 1 times 10 to the negative 7, isn't that actually equal to negative 7? Sure. We're just going to take the exponent of it. Now the 1 is in front, so therefore it's just 10 to the negative 7. But we're going to do the negative log. The negative log of this number, what it does is it makes this positive. So all I'm doing is taking the positive value of this exponent, all right, or I'm stuffing this entire number into an exponent. Don't fall in love with the idea of just taking this number and creating positives. Now, what did I just do? Well, my friend in chemistry, I just created a pH. That's what I just did. Little p means negative log. Now, why? Why? Because I want to take this number, which is pretty unmanageable, that's pretty cumbersome to write around, and take this expression, which can be cumbersome, and stuff it into an exponent. And it is by convention. So someone said it'd be a nice way to talk about what? pH in terms of a logarithmic scale in this case. So by the way, a pH of 7 is when you have equal amounts of H pluses and OH, and that would be pure water. Okay? And we'll talk about that being a neutral pH. Now, I'm not going to stop there. The pH is equal to 7. What if I take the negative log of the hydroxide concentration and make it into an exponent? Again, base 10. Well, we're going to 10 to the negative 7. What would be if you take that entire number, which is really here, and create that into an exponent, that would also be negative 7. But negative log means I times it by negative 1, and I make it a 7. This would be called the POH. Leslie, not as often heard of as a pH, but nevertheless it exists. There's the POH. Now, just to show you something, this is called KW, and what I'm going to do is take the pKW. Now, I'm going to do the negative log of this, so I'm negative logging everything. Negative logging the H plus concentration, which everyone understands as a pH, and I'm taking the negative log of KW, which winds up being 14. And notice something here. As I'll get rid of these values, this is the pH, this is the POH, and we'll write that here as the pH. Little p means negative log, so negative log of the H plus ion concentration, POH. Negative log of the hydroxide concentration, and this is the pKW, negative log of the KW. Now notice something. When I multiply these values, what do I get? Well, I get 10 to the negative 14, but what if I was to just take the exponents? When you multiply numbers with exponents, don't I add? Negative 7 and negative 7 give me a 14. Well, since these values are exponents, and I'm multiplying these numbers, this becomes what? Well, those are ugly squares, so let's get rid of them. That becomes the pH plus the POH equals the pKW. Or the pH 7 plus the POH, which is 7, equals 14. So that's an important value, and you notice the pH scale is based usually on a 0 to 14 scale because of that. All right, now we went from the actual concentration to the pH, but what if I want to go backwards? What if I want to go from the pH back to the actual concentration, whether it's the whole number or the scientific notation? What if I want to go back from a pH? What did I do? Going down, I created an exponent base 10, and that's called a log. I did a negative log to make it positive. How do I go back from an exponent back to the actual number? Well, some people call that the antilog, but we're going to do 10 to the x. Now, what does that mean? Well, remember, these are exponents. So if the pH is 7, isn't that really 10 to the 7 to go back? Now, I don't want to do 10 to the 7 because I want to go a smaller number, so we do 10 to the negative x. So 10 to the negative x. So all I'm going to do to go back to my number is go 10 to the negative x. And on your calculator, most calculators have a log key. Log key means you're going to stuff your entire number into an exponent base 10. And then under that log key, or on the second functional log key, you'll see 10 to the x. But we will do negative x to go back because we want our number to go back into a small number. We did negative log this way. We do 10 to the negative x to go back. And let me explain what I'm talking about. If you take out your calculators, let's say I have a concentration to be 2.32 times 10 to the negative 6. And that's my hydroxide ion concentration, or my hydronium. And I ask you, hey, what's the pH? How do we deal with this? Well, take your calculators, type in 2.32. Now, I like to use the EE key, not the caret key, but whatever works for you, negative 6. Now, what I'm going to do is I'm going to take the negative log of this. So I hit enter, and now I'm going to hit negative log. If you're using a TI-84, it's second answer. And what I get is a negative log of this. I get a pH that's 5.63. I did the negative log. I stuffed this entire number into an exponent. Terrific. Now, what if I want to know what the hydroxide concentration is? Certainly there's other ways, but if I know the pH equals the pKw, which is 14, couldn't I find the pOH? Right? I'm trying to find this concentration. I want to find the hydroxide concentration. So what I'm going to do is 14 minus 5.6, and I get 8.37, let's say. Now that's my pOH. Not something you hear too often about, but that is the negative log of my pH. Now if I want to get my hydroxide concentration, I want to take this exponent, right? Isn't this really 10 to the 8.37? Yeah, I want to turn that back into the number. So I do 10, I'll do negative x because, remember, I negated it down this way. I want to bring it back to the same small number. So I do, very simple, I did my second function if you have a TI-84, and I have a 10 to the x key, and I'll do negative 8.37. It's an exponent. And what I get for my concentration of hydroxide is 4.2, let's round it to 7, times 10 to the negative 9. And if you haven't already figured out, you could multiply these two numbers, and of course they would equal what? 1 times 10 to the negative 14, which is kW. So you said, Mr. Grodsky, if I wanted to find the hydroxide, why do I have to go through all this method? Couldn't I have just taken this or this number and divided by the H plus? Sure, you could. But I was showing you how you can work back and forth from pH to pOH. Now we measure the pH quantity or the H plus quantity by looking at the pH. We could have used the pOH, but by convention, everyone looks at pH. Now let me explain this for a second. All right, let's go back to our simple equation. H plus or H3O plus times our hydroxide equals our 1 times 10 to the negative 14. When we had equal amounts, this was 1 times 10 to the negative 7, and this was 1 times 10 to the negative 7. So when you have pure water, we have equal amounts, as we talked about. And this would give me a what? A pH of 7, which we say is neutral pH. Why is it neutral? Because we have equal amounts, H plus equals hydroxide. Now, watch what I do here. I'm going to increase hydroxide concentration 100 times. 1 times 10 to the negative 7 becomes 1 times 10 to the negative 9. I'm sorry, negative 5. So by increasing this 100 times, because it's a base 10 exponent, this number got bigger. 10 to the negative 5 is 100 times bigger. Remember, this is a difference of what? 10 to the 2, 100 times. So it's a difference of 2 exponents. And negative 5 is closer to 1 than negative 7. So you have to see that 10 to the negative 5 is bigger by 100 times. Now wait a minute, what's going to be the hydroxide concentration? This is still 1 times 10 to the negative 14. Well, 5 plus what is 14? What is it? 1 times 10 to the what? 9. Negative 9. Now what's my pH? If this is the concentration, pH, my friends, in chemistry is about the H+. What's my pH here? You haven't guessed it, it's a pH of 9. So when I have a pH equal to 9, it is not neutral. It is called a basic pH. Anything that is greater than 7 is a basic pH. Now look carefully, who's winning? If the pH is 9, okay, that means that this number is bigger. The hydroxide concentration is bigger. So at a pH of 9, the H plus or the H3O plus is less than the hydroxide. So anytime you have more hydroxides than H pluses, your pH is higher. Notice, as this number, H3O plus, is getting smaller because this number is getting bigger, it's an inverse relationship because you equal to a constant, which kind of reminds us of what? Pressure times volume equals a constant, right? Hey, inverse. Hey. Okay. Any case, as one goes up, the other one has to go down. So as this gets bigger by 1,000, this got small. Gets bigger by 100 times. This one got smaller by 100 times. Look at that. The pH increases, but the H plus got smaller. Why? Because a smaller negative number is a higher integer, right? 1 times 10 to the negative 10 is smaller than 1 times 10 to the negative 9. Now let's do this another way. Let's start again, and let's increase the acidity 1,000 times. So I'm going to increase this 1,000 times. Can you guess what the value of the H plus ion concentration, or H3O plus? You'd say 1 times 10 to the negative what? 4. Now why 4? 7 and 4 differ by 3. Well, 10 to the 3 is 1,000. So this got bigger by 1,000. What must be the hydroxide? 1 times 10 to the negative 10. It got smaller by 1,000. What's our pH? Our pH is always about the H plus. Negative log of that is a pH of 4. So when the pH is 4, we say we're in an acidic solution, or an acidic range. Anything below 7 is acidic. Why? Well, party people, when this number is bigger than this number, I shouldn't circle those, when the H plus ion concentration is bigger, this exponent has to be smaller. Think with me for a second. This number is going to get smaller. Because we're dealing with negative exponents, the smaller the number, the higher the integer behind the negative. So it makes sense. As pH drops, the number gets smaller. I would say that the exponent gets smaller. The negative in front makes this a bigger number. So as this exponent gets smaller, it really means you have more what? H pluses are greater than hydroxides. And that's how pH is explained. All right? Hopefully you can understand some of the basics here, no pun intended, of how pH is made and how it works and how we're going to work with it. And that's what we covered during this lesson. Thanks.